Today we will take up lecture 11, which is a continuation of lecture 10. In lecture 10 you may recall that we had discussed properties of surfaces, namely the first moment of a given area. We were concentrating on plane areas, and then from first moments of plane areas about x axis and y axis, we could find the centroid of an area. Now, towards the end of our last lecture, we had started with theorems of Pappus-Guldinus, and we were discussing the surfaces of revolution and volume of revolution. Let us try to recap that. The surface of revolution is obtained by rotating a curve about an axis. I will show you a simple example here. Suppose we have an arbitrary curve and one axis. Now, keeping the curve in its position vis-a-vis the axis, we will rotate this curve around the axis as shown over here. So, this whole curve is going around the axis, and the lowermost position it will be something like this, and then it will come back. So, in this process we will be generating a surface, a kind of conical surface for this figure. This surface is called the surface of revolution, and similarly we can talk about volume of revolution. Again I will show you an example. Suppose we have a planar area which consists of the boundaries of this area are a straight line and a curvilinear portion, and about the lower edge of this area you may imagine that we have cut out a cardboard piece of this shape, and at the lower edge of the cardboard piece we have attached a kind of axis or an axle, and around that axle this cardboard is being rotated. So, the volume so generated is the volume of revolution. So, after having understood how to generate a surface of revolution and a volume of revolution, the theorems of Pappus and Guldinus help us to find out, number one, the area of the surface of revolution in terms of the centroid of the curve which generated that surface of revolution. And in theorem number 2, we will be doing the similar thing for the volume of revolution. The volume of revolution will be determined in terms of the centroid of the generating surface of revolution. So, let us take these theorems one by one. Well, first I will take up the theorem which relates the surface of revolution with the centroid of the revolving curve. The theorem reads like this: the area of the surface of revolution developed by revolving a generating curve about the axis of revolution, both being coplanars. So, once again we are focusing our attention only on those curves which are in the same plane, they are not leaving this plane, and secondly the axis about which the revolution is being done or it is being rotated, that axis also lies in the same plane, is equal to the product of the length of the generating curve and the circumference of the circle formed by the centroid of the generating curve during the process of revolving the curve. So, let us go to the figure. Here is a generating curve, an arbitrary curve which may be smooth or it may be piecewise smooth, and this generating curve is being revolved around this axis which we are taking x axis, and during the revolution the surface is being generated. Now, in choosing the surface, the curve of revolution, we have to take some precaution. The generating curve should not intersect the axis. It should not pass or cut the x axis. At the most, it can touch tangentially the x axis. Okay? Otherwise, you will have a positive and negative surfaces, and that complication is not necessary at the moment. Well, the proof is also very simple. We consider a small element of the curve of which is being revolved. This the arc length of this small element is dl, and as it is being rotated, this dl will generate a ring shaped surface. Now, to find out the area of this ring so formed, we will have the circumference into the width. Width of this ring is dl, that is the arc length of the curve, and the circumference is 2 pi r. R is the radial distance from the axis, which is simply y, as you can check it again. This is y, this is the radius of the circle, and the width is dl. So, the surface area of the ring shaped surface is equal to 2 pi y dl, and if we integrate it from end to end on the generating curve, then the total area so generated A is equal to 2 pi y dl in line integral. Now, this is the definition, if you recall from lecture 10, of the y coordinate of the centroid of the generating curve. So, so this integral will be equal to yc into L. So, the total area will be equal to total area of revolution will be 2 pi into yc into L, where L is the length of the generating curve and yc is the y coordinate of the centroid of the curve. Okay. Alternately, we can state that the area of the surface of revolution is 2 pi times the first moment, that yc into capital L or line integral of y into dl is the first moment of the generating curve about the axis of revolution. So, both ways we can understand this theorem. Now, let us move to the second theorem of Pappus-Guldinus. Well, before I do that, let me mention that if your generating curve consists of several segments of different lengths, then or different orientations, then again the surface of revolution can be obtained. Area of the surface of revolution A will be equal to 2 pi times the summation. We will conduct the summation on all the segments, Ly, that is the length of the segment, times the centroid of that length. Maybe at this moment I can show you an example which we will be doing later. Suppose I consider this example which consists of a generating curve which has 3 segments. Segment number 1, which is a vertical line, segment number 2, which is a slant line, and segment number 3, which is the vertical line again. So, what we will do, that if we rotate this C shaped, you can say it is a kind of a C shaped body, wire bent in the form of C, then if you rotate it about this z axis, then it will generate the frustum of a cone. That is, it will have one surface over here, second surface over here, and the third surface will be this slant surface. Okay. Now, the radius of the left hand surface or end will be equal to R1, right hand end will be R2, and the length of this slant surface will be this length. Now, the calculation of the surface area can be very conveniently carried out in a tabular form. 1, 2, 3 are the 3 segments. Now, the length of segment number 1 is R1, the centroid will be at the mid height R1 by 2, and the length into that height will give me height of the centroid will be giving me R1 into R1 by 2. So, this will be R1 square by 2. Then we come to the slant length, which will be by Pythagoras theorem R2 minus R1 square plus the dimension h. So, plus h square whole under root. So, this will be the hypotenuse of this triangle, and the centroid will be at the middle point. So, the height of the centroid will be easily obtained R1 plus R2 by 2, and then you multiply this length by this height of the centroid, you get this expression R1 plus R2 over 2 whole into square root of the hypotenuse, okay? Yes, into the length of the hypotenuse. And similarly for the third segment, segment number 3, again length is R2, middle height for the centroid R2 by 2, and then R2 square by 2. So, all the 3 lengths, all the 3 L into Y, they have been determined, and if we add up, we will get the total area, which will be 2 pi times the addition of the last column, the addition of this last column. So, this is a very simple way of calculating the total surface area of the frustum. You can do it otherwise, but from geometry it will be much more complicated. Now, let us go back to the second part of Pappus-Guldinus theorem, which will relate the volume of revolution with the area of the generating surface. Well, let us see the statement of the theorem. The volume of body of revolution developed by rotating a plane surface about an axis of revolution, again both of them, the surface and the axis are lying in the same plane, that is very essential, is equal to the product of the area of the surface times the circumference of the circle formed by the centroid of the surface. Okay, area times the circumference of the centroid generated by the centroid during the generation of the body of revolution. Again, the precaution is similar precaution as we have for the first theorem. The axis of revolution either does not intersect the surface or it intersects only as a tangent to the boundary. Okay. So, the statement is that the volume of revolution is equal to 2 pi times the y coordinate of the centroid times the area of the generating surface, and if this is in piecewise segments, then we can do the same thing as we did for the first theorem, 2 pi times the summation of the each of the areas times the corresponding centroid, height of the corresponding centroid from the axis of revolution. Again, best way to illustrate the use of this theorem is to take up an example. This example shows an area, a planar area, which consists of a straight line, slant, a horizontal straight line, and the quadrant of a circle. Okay, this is the quadrant of a circle. This area, this shaded area, is being revolved around this x axis. The various dimensions are given. This is 3 meters to this should be 2.5, I believe. This will be 2.5 meters. Let me check. No, 2.4 meters, and again this is 1.5. So the obviously the height of this will be also 1.5. So this dimension is because this is arc part of a circle, first quadrant of a circle. So find the centroidal coordinates. Now here we have been asked to do the reverse thing, yc of the shaded area using the theorems of Pappus-Guldinus. So since by the statement of this theorem the total volume is equal to 2 pi times yc times area, so yc will be equal to V divided by 2 pi times the area of the surface of revolution. Let us do again very simple. Volume consists of, well, when the I will go back to the figure. When it is revolved, this slant length will generate a cone, okay, and when this segment will generate a cylinder, and this segment will generate a hemisphere, okay. So we have to find out the volumes of these three geometrical figures. For the cone, you know, the volume is equal to 1/3 of the base area, pi into 1.5 whole square into the length or height of the cone, that is 3 meters. Then for cylinder, pi r square into length of the cylinder, so again very easy. And then finally for the hemisphere, you will have because it is half of this spherical body, 1/2 4/3 into pi into the radius cubed. So this after calculation gives me 31.1 meter cubed, cubic meters. The area of the generating surface, which consists of a triangle, a rectangle and a semicircle, a quadrant of a circle, sorry. So it will be 1/2 into a base into altitude. Base is 3 meters, altitude is 1.5. So this is the area of the triangle, this is the area of the rectangle, 1.5 into 2, 2.4, and this is the area of the quadrant of a circle, 1/4 pi into r square. So this comes out to be 7.617 meters square. And if I divide the volume by this 2 pi times the area, then I will get the height of the centroid of the given surface, generating surface. So that will be 0.65 meters. So we have seen that with the help of the theorems due to Pappus and Guldinus, we can correlate one type of figure with another next hierarchy of the figure, provided it is generated through revolution. Now so far we have discussed the first moments of the area, and from that we determined the centroid of the area, and then came the theorems of Pappus and Guldinus. Now we will go to the next quantitative measure of the properties of a given surface, that is the second moment of area. Okay. So let us take up by the definition of the second moment of any given area. Again we will focus our attention on to coplanar areas, that is the areas which lie in the single plane, no shell like surfaces will be considered here. So then we define the second moment of area about x axis, that is I x x is equal to y square. remember Ixx will have y square area integral over the entire area, given area. So, y square dA integrated over the entire, this is the area integral. Similarly, Iyy, that is the second moment about y axis, will be the integral x square dA, that is the distance from the y axis squared integrated over the entire area. Now, some important properties or features of these moments are: number 1, Ixx and Iyy are always positive and greater than 0, because they involve square terms. So, whether it is a negative quantity or a positive quantity, square will always be positive, and unless the area is 0, that is it is just a point, the surface and 0 dimensional surface, the quantity will be non-zero. So, remember, in the case of first moments, the quantity could be positive, negative, or even 0, that is first moments about this axis of symmetry came out to be 0. But in the second moments, you will not get a 0 as this second moment of area, you will only get positive numbers. So, that is a very important result to understand. The first moment is entirely different in that aspect. Secondly, the elements of area farther from the axis about which we are taking the moments, whether it is x axis or y axis, they contribute much more than the nearby elements. Okay. As you go farther and farther, the contribution of that element of the area will be more and more, not even linearly, but quadratically more. And the third is the values of Ixx and Iyy, they are very sensitive to the choice of the reference coordinates. You recall something from the first moments. There we showed that whether the coordinates have been rotated or translated to another point, the coordinate of the centroid was unchanged, or the location of the centroid was unchanged, although the numbers may be different, but when you plot those values of xc and yc for different choices of coordinate frames, the location of the centroid will be invariant, it will be the same location, but here the values will be different for different choices of reference coordinates. So, these three features have to be thoroughly understood and compared with those of the first moments. Next definition is about the radii of gyration of a given area. It is again a new feature. We will define the x radius of gyration, that is kx, is equal to the moment, the second moment about the x axis divided by the total area taken square root of, and similarly for ky, that is radius of gyration about y axis is equal to Iyy divided by a whole under root, or alternatively I can write that Ixx, the second moment about x axis, is the total area times the radius of gyration about x axis, that is kx whole square. Similarly, Iyy will be a into ky square. Now, what is the physical significance of kx and ky? For the purpose of calculating the second moments of area, you can treat as if the whole area, given area, is concentrated at the at a point whose coordinates are kx and ky. Okay. So, that is if you shrink or degenerate the whole area to a single point whose coordinates in the given coordinate system are kx and ky, then area times the distance along x axis square, that will give me Ixx. That area times distance along the radius of gyration about the y axis ky square, that will give me Iyy. So, just like in the centroid have played the role that the whole area can be concentrated at the location of the centroid for the purpose of calculating the first moment. So, the role of kx and ky is a counterpart for the second moment. And then third thing which is of importance for the area is the product of area. Here it is a mixed quantity x into y integrated over the area, alright. Now, this quantity, because there is no square involved, it is just a product which can be positive or negative in value, or when you integrate it, partly it is negative, partly positive, and they both these positive components and the negative, they balance out each other, then the value of Ixy will be 0. So, this product of area in contrast to the second moment of area can be positive, negative or even 0, whereas the second moment of the area was always positive and non-zero. So, please remember this distinction. Now, let me take up an example. An area is given, the base of this area is 10 millimeter and it is along x axis. Along the y axis, the height of this area is obtained by intersecting with this curve, and the equation of the curve is y is equal to x squared divided by 10. So, two straight lines and a curvilinear line. So, you can call it a curvilinear triangle. This area is given, for which we have to find out Ixx, Iyy and Ixy. First of all, let us find out what is the area itself for this curve. You can easily see that if I take a strip, a very thin strip of, although it is shown bit thick, but actually it is a very small thickness, dx is a very small quantity. So, it is a thin strip going from the base to the intersection with this curve. So, the area of this shaded area of this strip will be the height times the width dx. So, height is y. So, and then we integrate it, y dx is the area of the strip, integrated from the left hand end to the right hand end, that is from 0 to 10, and for y we substitute the equation in terms of x. So, x square by 10 is equal to y. So, it will be integral of x square by 10 dx 0 to 10, very simple. You get the x cube by 3 into 10, so 30. So, 0 to 10 you will get 33.33 millimeter cubed. So, the dimensions of the area millimeter square, sorry, area is millimeter square. Now, we will consider Iyy, that is the second moment about y axis. So, we will again have dA will be y into dx into the distance from the y axis, that is x coordinate, and this x coordinate is uniform, same for all the height of this strip. So, x square into y dx. So, you will have x square into y dx, this is the area of the strip, this is distance square, integrated from 0 to 10, again substitute for y is equal to x square by 10. So, you will have x 4 by 10 integration from 0 to 10, and very simply you get 2000 meter 4 millimeter 4 power 4. Okay. Now, next we calculate, we have to find out Ixx and Ixy. That is, Ixx will be the area of the strip into the distance from the x axis, that is y itself, and this distance is varying along the strip. So, the strip method cannot be used, because this distance from the x axis, the normal distance from the x axis is varying along the location in the strip. So, we have to use the more fundamental definition of the area integral, that is in terms of a small element of width dx and height dy. So, then it will be y square, dA will be replaced by dx into dy, and what will be the limits for, let us say, x. X will, suppose I take up any point on this point. So, this will be varying along x axis from this point to this point. So, on this the distance x is equal to 10, and here it is obtained by the equation, that is 10 into y square root. So, the limits of integration are very crucial in this case. It will be 10 y under root to 10, that is from this point to this point, right. And then after having conducting the integration, then we will for x, then we will have the integration for y. Okay. So, first integration on x will give me simply x. So, we will substitute the upper limit and the lower limit. So, 10 minus 10 root 10 y into y square and integrate on y. So, again not a very difficult integration which you can carry out, and we will get 476.2 millimeter power 4. And last of all, we will have the product of the given area, curvilinear triangle. Again, we can't use the strip method because x is varying. So, we will use the small element, again dx dy into xy, and again you have the lower limit, upper limit, lower limit, upper limit for y, and without spending too much time you can get the final answer as 833.33 millimeter 4. Here it is positive, but for some other axis it can be negative. So, we have seen this second moments and the product of an area can be obtained very conveniently with the help of integration. Now, let us go to another very important part of this lesson, transfer theorems for second moment of an area. Suppose you know the second moments, that is Ixx, Iyy and Ixy about a given frame of reference, that is xy coordinates, z being perpendicular to the plane of the area. We are working on plane areas only, right. And you choose another coordinate axis, and the question is, do we again go through a fresh integration process to calculate the second moments about the new coordinate systems, or with the help of the old coordinate system or earlier coordinate system can we get some results? The answer is yes, it is possible to, if you know the second moments of a given area about the axis which is passing through the centroid, okay, then you can find out the second moment about a parallel axis. One is the given axis passing through the centroid, second is the parallel axis in terms of the second moments about the first axis. So, it can correlate the two. This theorem will be how to correlate between two parallel axes, provided one of them is passing through the centroid of the area. So, let me read out. If the second moments and the products of area are already known about the axis passing through the centroid of the given area, then it is possible to calculate these properties about the new set of axes. And for this, we will, let us say this is the given area, and one set of axes, this blue one, x dash, y dash, and z dash is coming out of the plane of the screen, is passing through the centroid C of this area. And then a fresh set, xy set, again z axis is coming out of the screen, is considered. So, I xx about this new axis can be related to I x dash, that about the old axis, in terms of the distance between the two and the values of the I x dash, x dash. So, for this purpose we will consider a small area as shown over here, okay, and its dimensions are dx and dy. This area is at a height y along the y axis from the x axis and y dash from the x dash axis. So, from the figure it is easy to see that y is equal to y dash plus the normal distance between the two axes, namely d. So, y is equal to y dash plus d, and then we use the definition of I x x, namely area integral of y square, and for y square we substitute d plus y dash and expand this bracket, we will get area integral of y dash square 2 times the area integral of d times y dash, and d square, d being constant has been taken out, d square times dA integral, area integral. Now, I can easily recognize two of the terms, that is, this will be I x dash, that is the second moment in the old coordinate system about x dash axis, and this last term is, of course, d square being constant as such, this is the area of the given figure. So, capital A times d square. Now, the middle term or the second term, 2 into d, d being constant taken out, into y dash area integral. Now, this quantity is known to us. Why? This is the yc, that is the y coordinate of the centroid, okay, in the old coordinate system, that is in the x dash y dash coordinate. So, the centroid in the x dash y dash, since x axis, x dash axis lies on the centroid, so the y coordinate will be 0 obviously. So, this integral will be 0, being yc dash, you can say, right. So, collecting the terms, I x x is equal to I x dash, that is in the old coordinate system, plus a times the normal distance between the two parallel axes squared. Similarly, for y coordinates, I y can be written as I y dash, that is the second moment about y dash axis in the old coordinate system, plus the total area times the normal distance between y and y dash axis. Let it be E, the normal distance between the two parallel axes is E, then this quantity will be AE square. Now, in general, we can say that the I about any axis is equal to I about a parallel axis passing through the centroid plus the total area times the normal distance square. This is called the parallel axis theorem for the second moments of areas. If we want to do similar thing for the product of an area, again I am taking an arbitrary area, the coordinates x dash, y dash are both passing through the centroid. So, you can say the centroid is the origin of this old coordinate system, x dash, y dash and z dash coming out of the plane of the screen, and a new coordinate system. So, that x is parallel to x dash, y is parallel to y dash, and this may be having any origin, let us say O. Okay. The origin of this is centroid, but this can be arbitrary origin. So, you see the normal distance between y and y dash is E, normal distance between x and x dash is D. Then the product of the given area I x y by definition is equal to area integral x y o dA, and this again we can substitute in terms of the old coordinates x dash plus the normal distance between the two y axes into y dash plus the normal distance between the two x axes integrated over the entire area. Again simplify this bracket and we will get this quantity, the product of area in the old coordinate system, that is x dash y dash and area times d into E. Then these two middle terms which will be x dash area integral, y dash area integral, and these are nothing but the centroidal coordinates in the old coordinate system, that is x dash c and y dash c. Since the origin, that is 0, 0 point is located at the centroid, so this quantity as well as this quantity both are equal to 0. So, these two middle terms are 0 quantities. So, we can say that these contributions vanish, and finally I x y is equal to the corresponding term in the old coordinate system, that is I x dash y dash plus an additional term a times the product of the normal distances between the corresponding coordinates axes. Okay. So, with the help of these two theorems or these two formulas, we can go back and forth between the two sets of coordinate second moments and product of areas, provided one set of coordinate axis passes through the centroid. That is very essential. You can't take just any two arbitrary parallel axes. One of them must go through the centroid. Let us say how we can apply this theorem of parallel axis. This can be very useful. Suppose the geometry of the area is quite complex and the integration will be very complicated, it will take a lot of time and sometimes you may have to resort to numerical integration. So, in such cases, if we can use the parallel axis theorem as I will be illustrating, then it will be very convenient. I take up an example to illustrate that. Suppose here is a kind of rectangular annulus, that is, this is the outer boundary and this is the inner boundary. So, the area of concern or in question is this shaded area. Well, technically such an area is a box section. In aircraft industry and in many other applications, a box like structure is quite conveniently or quite usefully employed. So, you have a box like this, and for the sake of simplicity, these corners we will neglect. We will say that it is a rectangle, outside rectangle and inside rectangle. Okay. So, the outside rectangle has the dimensions b and b, that is a square, and inside rectangle has again a and a, right. So, this is simplified like this, that is, you have two rectangles verticals and two horizontal rectangles, and you can easily see that this rectangle is symmetrically placed to this rectangle and this rectangle is symmetrically placed to this rectangle. So, whatever the contribution of this rectangle about the middle axis will be the contribution of this, and similarly whatever the contribution to the second moments of this, same will be over here. So, I need to consider only one pair, the other pair will be just a repetition. Also, as I said, it is a square body from inside as well as outside. So, whatever I get Ixx, and if I rotate it through 90 degree, I will get Yy. So, there will not be any difference, right, because of the symmetry through 90 degrees. So, my task is very simple, much simplified, namely we will have Ixx is equal to Iyy, and about the symmetry axis, the product of area is 0. We have already shown that if the axes are passing through the if the axis is a symmetry axis, then the product of area term is 0. So, let us say Ixy will be 0 about the symmetry axis, Ix axis and y axis, and Ix axis is equal to Iyy. All right. Now, we will call the vertical rectangles as area 1, yeah, this is area 1, this vertical, and the horizontal rectangle is area 2. Contribution of the vertical sub area to Ixx. So, first we are calculating Ixx. Now, this is the base into height cubed. Okay. This calculation, either you can find out the area of the second moment of area of a rectangular body from handbooks, or you can easily integrate it. You will find that it will be b, if you have a rectangle of width b and depth h, then bh cubed, that is width into height cubed or depth cubed divided by 12. So, this is exactly what we are doing. B is the width, is the depth, this is B, and this is B minus A divided by 2. Okay. So, B minus A divided by 2, this is the width into depth cube divided by 12. And since one rectangle on the left, second rectangle on the right symmetrically placed, the contribution is equal. So, adding up the contribution means twice. So, twice into 1 by 12 b cubed into the thickness of the rectangle, that is b minus a by 2. And if you simplify this, you will have very easily b cubed into b minus a divided by 12, right. And then we come to the horizontal rectangle, this rectangle, its width is now how much? It will be simply a, okay, and the depth is b minus a divided by 2. So, about this, its central axis, that is going through the mid thickness, it will be how much? a into b minus a by 2 whole cubed by 12, and then with the help of parallel axis we will transfer it over here to the x axis. So, that is exactly what we are doing. Well, factor of 2 is one horizontal rectangle above the middle plane and one below, contribution being same. So, we are taking twice 1 by 12 into a, that is width of the rectangle, into the depth cubed. So, this is the Ixx dash about the middle axis, and then by parallel axis theorem we will have a times d square. A is the area of the rectangle, that is width is a, depth is b minus a by 2. So, this product gives me the area of the rectangle times the distance of the middle of the rectangle from the x axis over here. This distance, this is the middle of this rectangle, and this distance. Okay. So, when you do this, you will get very easily this area. The rest is some simplification of these terms, and when you do this, you will get a by 48 b minus a cubed plus a into b plus a into b square minus a square by 16. So, this is the contribution of the horizontal sub area of the rectangle, and in the previous slide we have seen the contribution of the vertical sub area. You add up the two and you will get this as my final answer. And this I have already shown, this Ix is equal to I by y, because the body is symmetric when you give a rotation of 90 degrees. So, when x axis becomes y axis, it remains unchanged, and then the product of area due to symmetry is equal to 0, because the body is symmetrical about x axis as well as y axis. So, the product of area has to be 0, and that is the final answer. Okay. So, we have seen that a box like area, if you have to do it by integration, that will be quite a complex phenomena, because the limits of integration etc., will not be so easy to calculate. Even if you can do it, it will take a lot of effort. Here, with the use of parallel axis theorem, you can, and availability of some easy results, that is Ixx of a rectangle or a triangle or a circle, they can be easily calculated or they can be found out in any standard book. You can calculate the Ixx, Iyy and Ixy of complex geometries. Okay. We will take up another example. This example consists of you have to find the second moment of area of a rectangle out of which this hole has been removed, that is the net area is consisting of this as the outer boundary and this as the inner boundary. Okay. So, a rectangle and a circle. So, find the second moment of area of the rectangle with the hole about the base, about x axis of the rectangle. Also determine the product of area about base and the left hand. So, about x and y coordinates. So, I have to find out Ixx and Ixy. Again, we will use the parallel axis theorem. First of all, the net area consists of the rectangle of the side dimensions b into d. B is the width and d is the depth, okay, and a circle of radius r. So, the net area is area 1 minus area 2. and the second moment of a rectangular area we have already found out is BD cube by 12, but now we have to shift it to the base x axis. So, area into the distance of the center of the rectangle from the base, that is d by 2 square. Okay. You can see it over here. The middle of this rectangle will be somewhere here and this will be d by 2. So, you can calculate it, it will come out to be BD cube by 3. And then for the circle, let us go to the circle. For the circle, if you want to determine I axis about its diameter, then pi r 4 by 4. Again it is available in handbook, so you can easily integrate it out and find out. So, it is pi radius 4 divided by 4. So, this is the quantity I axis about this, and since it is passing through this centroid of the circle, namely the center itself, so I can use the parallel axis theorem between this, and the height of this will be d dash, which will be equal to this d dash can be found out, or sorry, it is given. So, pi r square into d dash square. So, if you simplify it, pi r square by 4 plus d dash square. Okay. And when you subtract the contribution of the circular area from the rectangular area, you get the I axis of the net figure. And to find out the I xy, the product of area, you can again do use the symmetry of the problem. So, about the new coordinates, you can easily see this axis is the axis of symmetry for the net figure. Alright. So, about this axis of symmetry, the product of area is 0, we have already shown, and then I have to transfer this to this y axis by parallel axis theorem, because the centroid of the net figure will lie on this axis of symmetry. So, I can use parallel axis theorem, and you can again see this I xy will be equal to 0 for the I x dash y dash, and this is the b into d into the location of the centroid. So, you can this is the contribution of the rectangle, this is the contribution of the circle. So, finally, we have this is b by 2 minus d by 2. Okay. So, this is I xy, the product of area about the centroid. One last thing, polar moment of area, that is, if you add up the I xx and I yy, then we get I polar, that is the polar moment of area, and by definition of I xx and yy, you will have y square area integral plus x square area integral. When you add up x square plus y square dA, so this becomes r square area integral. What is r? R is the radial distance of the element of the area from the center. Okay. So, this is called the polar moment of area. So, if the only thing is that Ix and Ixx and Iyy should be the second moments of area about the centroid, about the two orthogonal axes passing through the origin, arbitrary origin O. So, today we have seen the contributions made by the second moments of area and how to use the parallel axis theorem. In the next lectures, we will now start with the moment of inertia and product of inertia, which is quite similar in concept to the second moments of area and the product of an area. Thank you very much.